the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students who are just stepping into a topic called linear transformations. Prior to this, you should already have gone through pretty much all the prerequisite content, the setup content for linear algebra, which includes solving systems of equations, matrix equations, vector equations, row reductions, and you might have just finished up a topic called linear independence that is actually very important. Perhaps not for this conversation, but for future conversations. In this video, we'll focus primarily on just the definition of what a transformation is. And then in a future video, we'll turn our attention to linear transformations. But we'll start again with just the concept and definition of a transformation itself. So I'm going to actually read this, even though you possibly could read this as well, but I think it's kind of important to talk about. Up to this point in mathematics, you have significant experience with functions. Functions are going to be very, very important for our understanding of transformations. A function typically takes an input, x, and transforms, and I'm using that word on purpose here, it transforms that input into a single output we call f of x. Now, something you should note, that value of x that you're plugging into that function, f, is a single value in the real number system. Yes, there are functions that have as their input a collection of values. That is, their input is in r cubed or r squared or something like that. So it is very possible to have a function take an object or a point in Rn and transform that to a point in a different space. And again, I'm using the word transforms here on purpose. The set of all inputs for a function is typically called the function's domain. The set of all corresponding outputs is called the range of the function. And now we're going to turn our attention to something very similar for matrix vector multiplication. And this topic tends to throw students off. I had a student actually, just as an aside, but this is an important aside, so please pay attention. I had a student respond to one of my quizzes recently. I give these quizzes in my class, and every once in a while I will ask questions like, what did you find easy about this section and what did you find difficult about this section? And I had one of my students respond with a very insightful answer. And actually the answer was very predictive of what linear algebra actually feels like to most students. I was expecting this answer actually from a lot of students. I only got it from one, but I had other very common answers from other students. But this specific answer was very interesting. And it was this: I find it very difficult with all the definitions that we're learning. Some of them actually seem kind of the same, like we're using 3 different definitions for the same concept. And guess what? If you feel that way, you're not alone. That's actually a truth. For example, you have learned all about functions in the past, that they map an input to an output. They have a domain and they have a range. Well, when we start talking about structures other than kind of the elementary mathematical structures that you would have in maybe algebra and calculus, we change our wording. And so again, this is kind of the theme with linear algebra, is that you have several definitions for the same style of concept. It's not exactly the same concept, but it's very, very similar. So a transformation or a mapping, and notice we've already started with 2 terms for the same exact thing, of transformation or a mapping, and some people will call this a function as well. Anyway, a transformation or a mapping, which we will call T, from Rn to Rm, which we will denote as T colon Rn to Rm. Most people would read that the transformation T, which maps Rn to Rm, is a rule that assigns to each vector in Rn a vector in Rm, and that vector we'll call T of x. Now, let me go ahead and rewind the tape here so that we really grasp on and actually kind of align to previous knowledge. So if I traded out this word for a function, and you think about the definition of a function would normally have a name f. Function starts with the letter F, so we used the letter F. Well, when you're talking transformations, you use the letter T. Transformation starts with T, so we're using the letter T. Functions take an input. Normally, when you're working in algebra or calculus, that input is from just the real number system, R1. And it maps that value to some output also in the real number system, or R1. For example, f of x equals x squared is a function. You plug in a value from R, which is a set of real numbers, and you get out a value also in R, the set of real numbers. So that is our old school function notation and function definition in a way. Well, the only difference here is that the transformation maps from a larger space, so Rn, and it could map to a larger, the same, or a smaller space. That is, we could have a transformation that maps from R squared, so two-dimensional vectors, to, let's pretend, R cubed, three-dimensional vectors. And that can actually happen. You can take a vector, throw it into a transformation, and it transforms into a three-dimensional vector. You can kind of think of it as a function. It really truly feels like a function. You're taking an input, you get an output. This denoted statement here is very traditional in mathematics. When you have some type of rule or what we would call a mapping, you would use this notation right here. You'd have the name of the map. In this case, the name of the map is T, and you would talk about what space you're mapping from and what space your outputs will map into. So the space that we're mapping from, for example, might be R squared, and the space we're mapping into might be R cubed. Those are just examples. They don't have to be like that, and they don't have to be different spaces. It could map from R squared to R squared. That's actually more common. And then the rest of the highlighting here is very, very similar to the definition of a function. That mapping is a rule that assigns to each vector in your space Rn a corresponding vector, which we shall call t of x, just like for each input x for a function, there's an output f of x. And notice the output space here, Rm, is actually what we're mapping to in our transformation. So far, if you read this, you might think, well, that is no different from a function. And conceptually, it really is not. It's not that different, except that you use transformations for very advanced topics in mathematics, and it just works a lot better that way. Now let's continue forward and talk about those other words that we use when we talk about functions, domain and range specifically. And we're going to add yet another word, actually another two words into that language. So the set Rn, which is what we're mapping from, that set is called the domain of the transformation. That's the bucket of vectors, essentially, that you're grabbing from to plug into your transformation, to map to something. The set Rm is called the codomain, and that is going to be new to very many people, unless you had an incredibly theoretical course in maybe algebra or trig or calculus. The truth is that when you talk about a function, we know, going back to that good old example, f of x equals x squared, we know the domain of that is any real number, but actually the range of that is restricted. You cannot have negative values in that range because you're squaring the real numbers, and so they become non-negative. So the codomain is the bucket that contains all of these non-negative real numbers. So the codomain technically is the real number system. The range of this function would be the subset of the real number system that consists of all non-negative values. So the codomain is the big set, and the actual range is the smaller set. But you never really learned that in your algebra course, so it's forgivable if you did not know it. It's not that big of a deal, but the main thing is we reserve the word range for the actual set of values that are output by your function, or in this case, by your transformation. And we reserve the word codomain for the big space that contains all those values in the range. The vector t of x, and notice I said it's the vector because it is called the image of x under t. So just like, again, running back here to my simple example, if you were to plug in 3 to f of x equals x squared, you get an output of 9. And we call those with functions inputs and outputs. That's totally understandable when you're talking about functions. However, when you're talking about transformations, that right there is not commonly, but sometimes called an output, but really we call that an image. The image of 3 under the function f is how you would say that, or under the mapping of f. So in this case, you don't have to actually do that with your calculus course, so don't worry about that. But when you are in linear algebra, you definitely want to call the output the image. It's just important. And finally, the set of all images, so the set of all outputs, is called the range. And that's what I was saying a moment ago. Now, it seems like there's a lot going on here, but it should be very familiar to you. It should feel a little bit weird at first, but eventually it'll become very, very natural because it is so similar to all of your function conversations you've had in the past. And I have a visual down here for it. So we have a mapping here. The mapping has the name t. It maps from Rn to Rm. What you're seeing here is the domain, Rn. It's not really an nth dimensional space the way it looks. It looks like R2, but you can't really draw a 17-dimensional space easily. So let's just pretend that's Rn. And we have some vector in Rn. And we're going to transform that using transformation t. And when we transform that vector via t to a new vector, that new vector could land actually in Rn, but let's just pretend that our mapping is from Rn to Rm. Now notice that big old box there. That big box is very important. That big box is actually Rm. But notice the shaded plane, we'll just call that the shaded region, the shaded region that all values of x map to. That's a subset of Rm. So Rm is the codomain, and then all the values that x could possibly map to via t, that shaded region is called the range. So again, the range might be smaller than Rm. It's just a smaller subset, but it could be the entire space Rm. You just don't know until you actually are handed the transformation. And even then, you probably don't know until you do some mathematics. But that's a really nice visual. So far, all we've done is defined basically a brand new style of wording for the word function. Now, the note, if you have my lecture notes, this note right after here is everything that I just said. There is an important distinction to be made here. The range of a transformation is a subset of the codomain. You can see it in that picture. That range on the right-hand side is a subset of the box, which is the codomain. It is pervasive for people to think that the range is everything in Rm, but this is not necessarily true. I should not say that it's not true. It's just that it's not necessarily true. It could be true, but it doesn't have to be true. And now what we're going to do is an example that will showcase this distinction. Consider the transformation, which takes a vector in R squared and transforms it into the same space, but it might be transformed into a completely different vector, but it still transforms that vector into the same space, defined by mapping the vector x in R squared to the vector y in R squared by multiplying the first entry in x by 2 and the second entry by 0. Play with this using any vector in R squared and make a conjecture about the range of the transformation. So let's take a look at maybe like 3 or 4 different vectors in our R squared. And I'm just going to limit it to 3 because really all you need is that. You don't even need 3, honestly. What we're going to do is just create vectors. You can do whatever you want. but try to create a kind of a nice swath of vectors that you can play with here. So we'll do one just general, let's say -1, 5. And let's have another one that maybe has a 0 in the second element. So let's do like a pi 0. And then finally a vector x sub 3. That was supposed to be, by the way, vector x sub 2. Vector x sub 3, let's do a 0 in the top element. Notice I'm just using irrational numbers in those last 2 column vectors. All right, the mapping does the following. It takes that first entry in x and multiplies it by 2. And then it takes the second entry and multiplies it by 0. Showcasing the mapping, we'll say it's the mapping t that takes, well, we already know what it does. It takes r squared and maps it to r squared. But let's see what t does to x sub 1. Well, it's going to take double the first entry and 0 times the second entry. All right, well, I don't see a pattern there, but let's go ahead and continue forward. Let's see what our transformation does to the second vector. It doubles the first entry and zeroes out the second entry. And finally, the third vector. It doubles the first entry and zeroes the second entry. And if you start playing with this, you should start realizing that no matter what happens, the output will always have the second entry be 0. And so the conjecture here, make a conjecture about the range of our transformation. Our transformation is going to be the set of all vectors. I'll write it this way first. It's a set of all two-dimensional vectors such that the first entry is a real number and the second entry is 0. Now, if you think about that as a graph here, the first entry could be 0 and the second entry would have to be 0. The first entry could be 2. The second entry would still have to be 0. The first entry could be a -10, but the second entry has to be 0. No matter what, you're going to have vectors land on this horizontal axis. So this is actually the line going through the origin having a slope of 0, or basically the x-axis in r squared. Now I want to draw your attention to something. That range is actually not all of r squared. All of r squared is this entire plane, and yet the range is just a subset of r squared. R squared, by the way, is called the codomain because it is the bucket where our solution sets, or our vectors, I should say, lie. And since they're two-dimensional vectors, it's r squared. So the codomain is r squared, yet the range is just that horizontal line. And I kind of wrote it in a weird way. I said the range of t is a line of slope 0 going through the origin in r squared. Well, the reason why I write it that way is because if you graduate to higher dimensions here, it's really hard to say that it's the horizontal axis. That just doesn't work out with larger dimensions. So it's better just to say it's a line that goes through the origin in this space. So that's a basic mapping. Now notice I didn't use any other mathematics than a description of what the mapping does. So I haven't showed you, like in our previous slide there, or previous page, I didn't tell you what the function did explicitly mathematically like this. But there is actually a function in the background, or a machine in the background, that is doing the mechanics for us. Right now, we're just doing the mechanics by word. Just like if I didn't tell you what this function was, and instead I said, hey, I've got a function, and whatever you plug into it, the function's going to return the square of that, right? I didn't explicitly write down the function, but I told you the action the function would perform. So we used our brains and kind of developed some outputs. Same thing here. But trust me, this is just an introduction to transformations. We will actually get to the true kind of defined machines that are working in the background, and we'll do that in the next video. I hope that this was mostly understandable for you, if not all understandable for you. And I hope to see you in future videos. Please be a wonderful person.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.